should stop my sharing and then start recording, I think. I don't know.
It started recording.
Oh, it has started? It has started. Okay, let's hope that it's recording. Okay, and it has started recording, and you can see my slides, right? All of you? Okay. So yeah, so slam dunk. I'm a sports lover myself, so it's a term used in basketball, and when the player, run with the ball towards the basket, and sometimes you guys must have seen on the TV that they jump and with the ball in their hand they put it in the basket, right? So it's like, let me explain in Urdu that जैसे जबरदस्ती का नहीं आप बास्केट करते हैं एक तरह से, एक तो बास्केट है ना, आप दूर से बॉल फेंकते हैं और बास्केट के अंदर जाती है, बड़ा पोलाइट वे है। एक ये कि आप ठक ठक करते हैं, बॉल को लेके जा रहे हैं और उसके बाद बॉल पकड़ के आप उछलते हैं और बास्केट के अंदर ढस करके डालते हैं, ऐसा लगता है जैसे, हाँ वैसे लगता है जैसे जबरदस्ती आपने जोर लगा के बास्केट की, एंड देन यू नो स्टॉप देयर फॉर द फोटोग्राफर्स टू टेक पिक्चर्स। सो इसको स्लैम डंक कहते हैं। सो इज पैकेट स्विचिंग अ स्लैम डंक विनर? व्हाई वी आर मेकिंग दिस स्टेटमेंट? बिकॉज both have pros and cons. Packet switching and circuit switching both have their pros and cons. In circuit switching, let's repeat, in circuit switching you have a guarantee of bandwidth, you have a guarantee of delay, you have a guarantee of throughput, you have a circuit like behavior. Okay, whenever you want to use, you pick up your phone or whatever thing you are using for circuit switching, you will always get the same level of quality. You cannot say this in packet switching, even if you buy 8 MB or 16 MB of DSL. Now, same level of quality, no one can guarantee you the same level of quality. Okay, the problem is it is not good for resource sharing. With circuit switching you cannot accommodate a lot number of users, and the state maintenance and all those things. So what is ideal? Okay, so there are for the internet, yes, we can say it's a slam dunk winner, packet switching, because it's great for bursty data. It is simple, there is no need to set up the call, there is no need to maintain the state, and yes, then we have a congestion which is possible. We can have packet delay, we can have losses, and then we need protocols to cater for these things. जैसे we had a question in the previous class from Amjad. So we need protocols for to cover those delays and those losses. Okay, congestion control, reliable data transfer, things like that. Ideal scenario is that we use packet switching and we provide circuit-like behavior. This is the ideal scenario. Okay, we accommodate more number of users, but the behavior, but the response from the network for the user is circuit-like. Okay, so these are the closing remarks of this topic, and should have been closed before the break, but I think we discussed it in a bit more detail, and I had lots of questions as well. We have after the break, what the content that we want to cover is this one, and let me remind you that again, these things may be a brief recap for some of you, the first few weeks of the course, but the audience is very diverse. So I am going through these first 4-5 chapters of Kuros and ROS. Okay, and after that we will go into the advanced topics like software defined networking, some labs, and data center networking and things like that. Okay, it's mentioned in the course outline. Right, so the next topic is delay, loss, and throughput, and mainly we will try to cover delay. We are very interested in understanding the delays that happen in the internet, because these notions are something which we will define and understand today, but after that we will keep using them throughout the course, and even after the course, maybe in some other courses of networking and some other, so whenever you read some paper related to this field. So it is very important that all of us understand the types of delays and how they occur and what are the factors affecting those delays. Okay, so it is topic 1.4 in our textbook, Jim Kuros and Keith Ross, 6th and 7th edition. Okay, right, so it's the same slide once again that we discussed in the last lecture set when we were discussing packet switching. We are having this scenario that in which we have the incoming rate and then outgoing rate. I mean, packets are being queued over here. Okay, there are some of the free buffer slots available for the more incoming packets, and then the packet in the front of the queue is being transmitted and things like that. Okay, so what is a nodal delay? I mean, the delay that can happen at a particular node. Okay, So you can see here, and I mentioned it in the last um, in the last lecture as well, uh, that we have these four types of delays. Okay, we have dpros, delay, processing delay. We have dq, queuing delay. We have dtrans, transmission delay, and we have dprop, propagation delay. And if we define all these four types of delay, I mean, these are all the types of delays that can happen at a particular node. And please note that all these four types of delay will happen at each and every node throughout the path. So if we have 10 hops between source and destination, then we will have a d nodal for the first node, for the second node, for the third node, and up to for the nth node. And in each node, all these four types of delay will happen. Okay, and what are these four types? Let's get an explanation in the next few slides. So, first of all, the processing delay, it's the simplest one. Okay, dpros, the nodal processing delay, right? Um, I mean, just like the name suggests, the delay which is required by a device or a router to process the packet. Okay, and in processing, several things comes. So for instance, the device may have to check for bit errors. I mean, it may have to calculate the checksum or things like that. It may have to determine the output link. Okay, so for example, it have to uh, unwrap the IP header and then look into the destination IP and then decide which port to transmit. So determine the output length. And typically this delay is in the order of microsecond. And usually this is the delay which is very minimum, and you neglect this usually. Okay. The second delay is DQ. So queuing delay, the time waiting at the output link for transmission. And as we said in the previous lecture, the quantifying queuing delay is the hardest thing to do, and we don't have a generic formula for that. And it depends on the level of congestion at the router at any particular instant of time. Okay. We have the transmission delay, which is L by R. We just discussed again it in the previous slide. L is the length of the packet, R is the rate of the link, and then we have the propagation delay, which is the time required. So I mean, students do confuse transmission and propagation delay sometimes. Okay, yeah. So let me just give their definitions, and then on this slide I will mention using my mouse as an example. So transmission delay, I already gave the definition. I repeat again: the time required by the device or the router to push the entire packet from the first bit till the last bit on the link. And this delay is happening over here. Okay, when when uh, uh, when the when the device is pushing this entire packet right here, this delay is happening over here. Okay, so this packet is of length L bits, L bits, and let's say these are 1000 bits. So bit number 1 to bit number 1000, all these bits are being pushed over here one by one, one by one, one by one. Okay, and this is the time that this router will take to do this is L by R, which is the transmission delay. Then this packet will propagate from this router to this router over this link, and the time required for the packet to propagate on the link is the propagation delay. Okay. Okay, this is the propagation delay. So it is d by s, and d is the length of the physical link. This length, this particular length, this one, this is d, and it may be in kilometers. Okay, 200, 300, 400, 1000, whatever, in kilometers. And s is the propagation speed in medium. And by the way, speed of light inside fiber is 2 into 10 to the power 8 meter per second. So we can take that number as a reference. Okay, in our calculations. Okay.
Propagation delay is actually between the routers.
Between two nodes, yes. Between two routers, between two switches, between any two nodes. Okay, that is the propagation delay, and the transmission delay happens at the node when the node is pushing the entire packet from first bit till the last bit. Okay, so there is a clear difference. I hope it's clear to everyone. Okay, so these are the four types of the delays, and summing these all four delays, you can see over here in the formula, dpros plus dq plus dtrans plus dprop is the d-nodal. Okay, that's the nodal delay. That's the whole, the total delay that is happening at this particular node. Okay, right. Then there is this caravan analogy, and if everyone is clear on transmission and propagation delay, my experience of teaching this course, I should skip this caravan analogy because it was usually it confuses the students rather than clearing them up. Okay. So in this analogy, they are actually, taking this 10-car caravan as an example of a packet. They are saying that each car is a bit, and these 10 cars caravan is a 10-bit packet, and the time required for the toll booth to process this caravan one by one car, one by one, each 10 cars is the transmission delay, and the time required for the caravan to travel from this toll booth to the next toll booth is the propagation delay. So they are just giving the analogy. I hope everyone is clear on the difference between the transmission and propagation delay, right? Okay. Then the queuing delay. So as we said in the previous lecture as well, that quantifying the queuing delay is very hard. We don't have a clear formula. We have a formula. We usually neglect processing delay. We have a formula for transmission delay L by R. We have a formula for propagation delay D by S. And for the queuing delay, if we know the number of packets in the queue, we can quantify queuing delay. Just like I mentioned in the previous lecture, that if we know that there are 10 packets in the queue, the first packet will have 0, the second will have L by R, third will have, 2 L by R, and the 10th packet will have 9 L by R queuing delay. Amount of time it will be waiting in the queue. But generally, we don't know the number of packets being queued at the router. So how can we say that how much is the queuing delay? We cannot quantify, but we can say something like that when the queuing delay will be large or small. And we say this on the basis of this parameter. And this parameter is traffic intensity. Okay, right here. Traffic intensity, LA by R. And let me explain this. It's very interesting and very um, sometimes it confuses students, but it's very interesting. You should not be confused. Let's discuss it. This parameter LA by R. So if you notice, R we have it before. R is the link bandwidth in bit per second. Okay. L we discussed. It's the packet length in bits. A is the average packet arrival rate. Okay. A is the average packet arrival. So LA by R is something which is calculated over some period of time. Okay, over some minutes, some hours, even more than that. So LA by R is something which is being averaged out over some period of time. Okay, it's not something instantaneous, right? Instantaneous is something like if I look at the router, I know the number of packets. Okay, and then just like the example I gave you of the bank, I go to the bank and how many people are waiting, I can calculate the time I will be waiting in the queue. Okay, right? You guys know that. So there are 10 packets. How much time will each packet will wait? 0 L by R, 2 L by R, up to so on, n minus n by L by R. But that's instantaneous at a particular instance. How many packets are, but traffic intensity is something which is being calculated over a longer period of time, being averaged out. So listen carefully. I'm going to explain this and then I will give you guys an example. Okay, how we can do this. Okay, so if you notice, it is a unitless quantity L because LA, which is at the numerator. Okay, L is the length of the packet and A is the average packet arrival rate, which is usually in packet per second, right? If the length of the packet is in bits multiply by packet per second, so it's like bit per second, right? It is like bit per second and divided by R. R is already in bit per second, so it's a unitless quantity. It's a unitless quantity. Okay, there is no unit of LA by R. So and its value is usually hovering around 0 to 1, just like probability. But it's not probability, but the value usually goes from 0 to 1. Okay, why it goes from 0 to 1? If you look carefully, the product of LA is actually incoming rate. L is the length of the packet, A is the packet per second. So the product of LA is, how many bits are coming per second actually, right? So it's an incoming rate, it's the ingress rate, and R is already what? It's the outgoing rate, right? So LA by R means LA should always be either small or equal to R. If it is greater than R, then we are having the situation where packet loss will occur. We will have enormous queuing delay because LA is incoming rate, R is outgoing rate. Is the product of LA is high, then we will have more packets or more bits incoming, packets being queued, and if this stays for some even for a little longer, loss. Okay, So usually the correct value should be between 0 and 1. Now, it's mentioned over here, right? Again, there is no quantification. On the y-axis, you can say average queuing delay. We are not quantifying it. We are just saying that if LA by R, the product of LA by R is close to 0, is more close to 0, okay? Which means that the incoming rate is less than the outgoing rate. Uh, I mean, it will be close to 0 when LA will be small and R will be large, right? So in this scenario, we will have very, very low queuing delay, right? Queuing delay will not be much. It's average over a period, over a longer period of time, but the average queuing delay will be low, okay? But if as soon as this LA by R approaches to 1, it goes towards 1, the queuing delay, it will increase exponentially. So this is the parameter, the quantity, traffic intensity, which is controlling the queuing delay. It is just giving us an idea that LA by R approaches is approximately close to 0, average queuing delay very small. LA by R is approaching to 1, queuing delay is very large. So what we want to do is we want to maintain a balance of this quantity. Okay. Now this is how I explain this thing is in English. Now let me give you guys an example. Okay. And I will put a question, a very interesting question to you guys as well in this example. Okay. I'm going to write some numbers on the slide and then I will ask you guys a question. Let's say that the 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 average packet arrival rate A is 5 packets per second. Okay, let's say something like that, 5 packets per second. Okay, and let's say that that L is I don't know, 1000 bits, right? 1000 bits, the length of the packet, and R is uh, 1000 bit per second. 1 kbps. The link rate is 1 kbps, which means 1000 bit per second. Okay. So if we calculate the numbers, if I'm not wrong, I mean L by R will be 1000 divided by 1 second, something like that, or not. Uh, okay, instead of calculating, okay, instead of calculating, because I may have the numbers slightly jumbled up. Instead of calculating, let me give you some answers, and then because the interesting thing is I am interested in putting a question and getting a concept out of you guys, or the either way around, telling the concept to you guys. So let me say something like that the L by R, is 0.2 second. Okay, 0.2 second, right? I'm giving a number, so which means that and now if we say that A is equal to 5 packet per second, 5 packet per second, again so this product will be how much? 1, right? 1, because that means that 0.2 L by R is the transmission delay, right? And if the transmission delay is 1/5 of the second and 5 packets come in 1 second overall, average packet arrival rate, A is average packet arrival rate, the rate on average at which the packet arrives, it is 5 packet per second. In each packet takes 0.2 second to get transmit L by R. So overall, as you said, the incoming rate and outgoing rate will be equal. 5 packets come in 1 second, 5 packets are being transmitted. So the quantity LA by R will be equal to 1. Now I put a question to you guys. If incoming rate and outgoing rate is equal, then why we are saying that there is this amount of queuing delay over here? When it approaches to 1. I mean, if the number of bits arriving to the link and the number of bits leaving the link, they are all equal, then should there be any queuing delay? I mean, you are getting my point. If the same number of packets are coming in 1 second and the same number of packets are leaving, if 5 packets come in 1 second and 5 packets leave in 1 second, should there be any queuing delay?
Propagation delay.
No, propagation delay has nothing to do with it. You can ignore it. and you have to ignore it. It is when the packet comes on the link and transmit to the next node.
Processing related.
Again, neglect processing delay. Okay, you neglect processing delay, you neglect propagation delay. And my question is, incoming rate and outgoing rate are equal. Should there be any queuing delay? There should be not, right?
No.
No? Anyone from the DL mod? Yes. The point I'm trying to make here is that A is 5 packet per second, okay? Average packet arrival rate is 5 packet per second, and the transmission delay of a single packet is, in my example, I'm just quantifying for your ease, is 0.2 second, right? It's 0.2 second. So which means that the incoming rate to the link, okay, is actually 5 packets per second, and the outgoing rate to the link is also 5 packet per second, 0.2 times 5. So if the incoming rate, if the ingress rate and egress rate are equal, then why is a queue being formed? Will there be a queue? So, yeah.
Excuse me.
Yeah, 5x. Yeah. Yeah. Okay. Uh, let's say that the average of 5 packets per second is constant all over. Okay, yeah, from DL mode. Anyone? You started very well. I thought that you are about to nail it. Yeah, from DL mode. From DL mode.
Maybe there won't be a queue delay because obviously the amount of packets coming are leaving as well. So
Okay,
why
so
would there be a queuing delay? Since
that's
we are
my question
ignoring the
actually.
processing delay as well. Yeah, this
And
is
the
what I'm saying, that
propagation.
there
Yeah.
won't be any queuing
You're
delay.
saying that there won't be any queuing delay. Okay.
Yeah, that's what I think. Yeah.
There are 2 raise of hands. Yeah. Ali Amjad and Mohammed Iqbal. Anyone?
सर
Yes.
हमारे पास जो क्यों डिले होता है वो तब आता है जब वो पैकेट हमारे पास जब ट्रांसफ़र हो रहा होगा राउटर से। तो जैसे ही या तो क्यूइंग डिले हमारे पास 0 तब होगा कि हमारे पास क्यू के अंदर कोई पैकेट ना हो। तो अगर जब पैकेट्स हमारे पास क्यू के अंदर ऑलरेडी हैं, उतने ही हैं और उतने ही ट्रांसफ़र हो रहे हैं, तो हमारी क्यू तो खाली कभी नहीं हुई ना। तो इसलिए इसी वजह से मेरा ख्याल है कि क्यूइंग डिले हमारे पास मैक्सिमम आएगा।
चलें, thank you everyone for your answers. Let me you all are going in the right direction, all of you. But let me put it in my own words as well, to bring everyone on the same page. In this particular example, I'm going to say some sentences. If every packet is perfectly spaced L by R time to each other, if every packet is spaced perfectly L by R time, which means if we talk numbers, if every packet come after 0.2 second, if we guarantee that every packet come after 0.2 second, then there will be absolutely no queuing delay. But this cannot happen. Now you were going in the very right direction. The average is 5 packet per second, which means that 5 packets come in 1 second at the incoming link, and 5 packets leave in 1 second. But who knows how these 5 packets, if they are coming in burst, if they are coming in burst of 5 packet and then the whole second is silent. You are getting my point? Okay, let me give the bank example again. If 5 people are arriving simultaneously, then you cannot say that there will be no queue. But if people are coming at so regularly intervalled amount of time that when the first person gets served, immediately the next person comes to the bank counter, it will have 0 queuing delay, and each and every person will have 0 queuing delay throughout the day. But that doesn't happen. Okay, so the average is something else. Average is only telling us that 5 packets are coming in 1 second. Okay, but how these 5 packets are coming, whether they are coming one after each other every 0.2 second, then it will be 0 queuing delay. But no, if they are coming, 2 packets arrive, then there is silence periods of 0.5 seconds and then 3 packets arrive, we will have queuing delay. And generally, when we have LA approaching to R, equal to R, and the quantity approaching to 1, generally the queuing delay is on a higher side because of the bursty nature of internet and our use. Okay, I hope all of you get an understanding of this answer. Okay, and why the curve is like this. Okay, it's a very interesting concept. So the incoming rate and outgoing rate, even if they are equal, we will have some queuing delay and even a significant amount of queuing delay. The next slide just depict the end-to-end delay. So I have already told you guys, denodal is a delay happening at one node, another denodal at the next node, and if we sum all the delays of all the nodes, we will have the average end-to-end delay. Now I am going to, you know, give you guys one last slide, one last thing, or we can just one last thing. Okay, I will. So we started the topic. We discussed the components of delay, all 4 components of the nodal delay. Then we discussed end-to-end delay, and now we are going to discuss the real internet delay. One of my favorite topic to teach and one of my favorite tools to teach. We are going to use the traceroute program. I hope many of you might have used it before. Okay, we will use the traceroute program, and we will see that how traceroute calculate the real internet delay and how real internet delay will look like. Okay, so it's a utility. Traceroute is a utility that provides delay measurement from source router to destination router along the internet path. Okay, towards the destination, right? So this is the working of traceroute. I'm just going to skip it because I'm running out of the lecture time. But you know, what it does is that somehow with magic, the traceroute sends 3 probes, and the first 3 probes return from the first node, and then it sends another 3 probes, and the next 3 probes return from the second node. When we will study ICMP, Internet Control Message Protocol, we will see how this actually happens, how traceroute does this magic, that when it sends the first probes, it returns from the first node, the second probes return to the second node, and the third probe return from the third node, and the nth probe return from the nth node, and then ultimately from the destination, and then it stops. Okay, and obviously because it is sending probes to each and every node, it keep recording the delay of each and every node, and it produces an output of like this, an output like this. It's very interesting, very interesting tool. If you can see, it's a real trace route. It's a real trace route between University of Massachusetts and Eurocom France. So these are two universities which are in 2 different continents, and there is an Atlantic Ocean in the middle. Okay, right. So Gambia is on the west side, near Atlantic, near Atlantic. It's at Antarctic. So which means it's just like trace routing from Gambia to University of Massachusetts. Okay, so if you guys notice, it's this is the output of trace route. It just looked very boring and a bit complicated, but it is very interesting. Let me walk you guys through this output. There are 6 columns, basically 6 columns. Okay, so the first column is simply the node number or the router number. So the first router, the second router, third, fourth, and up to so on. 19th hop is the destination. Okay, so the first column is the serial number of the node. Okay, the second column is the name of the router. The third column is the IP address of the router, and the fourth, fifth, and sixth columns are the 3 measurements, the 3 probes that are being returned from that hop and recorded by the source node. Okay, so this is like this. The 3 probes to the first node are being recorded over here like this. Okay, and then the 3 probes to the second node, okay, are being recorded over here. And the reason of 3 probes is because internet is a packet switch network, delays keep changing. So to have a good average and good understanding, we at least send 3 probes to each node. Okay, so this is the output, and it's very interesting. If you guys note that you can have a look at how network is changing. You can see that we are in the University of Massachusetts right now. Again, we are in the University of Massachusetts here as well. Then we go to some access network. Okay, VBNS, I don't know, it's something in the US. And then Abilene, I know this network. This is the educational network of United States, Abilene, okay? And because this is a university, then that means it is using the service of Abilene, just like we are using the service of PERN in here. PERN is the Pakistan Education Research Network, and NUST is using the bandwidth from PERN, Pakistan Education Research Network. So Abilene is like the same thing in the US. And then you can see another node of Abilene in the Washington right here, okay? And then and then you can see that there is a significant amount of delay being added. So you can notice that this from node 7 to node 8 is where we go to the transoceanic link, undersea cable, the Atlantic Ocean. So it must be some 2000 or 3000 kilometers, and we have a significant amount of propagation delay, and it is added over here. So we can see that from 22 millisecond we jumped right to 104 or 109 millisecond, okay, right here. And then here is where we enter Europe. We don't know the name of the router, but then on the 9th node we know that it's GEANT, and GEANT is the European Research and Education Network. Okay, I know this network as well. And then we have the GEANT node in France. Okay, and then again in France, and then we reach the destination. Static means either the probe is lost or the router is not replying. Usually the router, they block the ICMP messages. They block traceroute or ping commands just to stay safe from the outer world. Okay, so it is quite normal if you traceroute somewhere and you get this static in reply. Okay, um, uh, yes.
Why are we using 3 probes?
Why not more? Why not less? 3 is a good average. I mean, as I said, that internet is a packet switch network. So packet switch network, the delays keep changing, and even here you can see that in these 3 different probes we have a slight variation in the answer. So for example, right here, if you see, you have 21 millisecond, you have 18, and you have 18, then 16, 11, and 13. So something like that. At each and every second, the level of congestion at different routers is changing. Okay. Sorry. So that's why 3 probe is a safe thing to do. We can average out the overall answer. Okay. And also something very interesting you can note, sometimes you get less delay from the next node compared to the previous. For example, can you notice this anomaly over here?
Yes, sir.
Right? In
11th,
11th,
10th and 11th.
10th and 11th. You're right. You're well spotted. Yes, you can see over here that we have 113, 121, and 114, and right here is 112, 114, 112, and another. You can see that on the 15th we are having 135, 128, 133, and the next is 126, 128, and 126. And why this happens? Again, the reason, all the variations in internet. Please remember, everyone, all the variations in internet when we talk about delays is only due to one component, and that is we studied 4 components. Queuing delay. The queuing delay is the delay which is always varying. You never know how much queuing delay the packet will incur. Okay, it always depends on the level of congestion the router has. So every time you see some sort of variation, okay, this is not wrong. This is totally right that we get 126 and then 135 and then 126 again. This is fine because the level of queuing, because these are all independent probes. These are all totally independent. 3 independent packets being sent, returned from first node. Another 3 independent ICMP messages being sent, returned from the second node. Another 3, another 3. So these are all independent probes recorded totally separately. Okay, so it is totally possible that we can have this sort of behavior. Okay, just conclude the DL mod students. Can you see my screen? I mean, my screen
Yeah.
is shared or the slides are shared? My screen is shared, right?
Yes.
Okay.
Yes.
So let's trace route. Okay, and to add an element of humor in it, I am going to trace route my alma mater, my university where from where I did my PhD and postdoctorate, and I will say the name in Italian. You can see the command prompt. You can see the command prompt. So trace rt www.polito.it. Okay, that's how the Italian will pronounce this the name of their website. This is Politecnico di Torino, from where I did my PhD. So www.polito.it. Let's trace route this site, and you can get answers. Okay, so first hope right here. We have delays like this. There is the name of the router is not mentioned. The IP address is there. And then we have no reply from the second router of I mean, it should be within seeks, but there is some packet switch or router in the seeks which is blocking the ICMP messages. Okay. And then we are here. We still don't have any name, so we can't really say where we are. But okay, there is still no names over here. We don't know the network where we are. But the delay is, is increased a lot, 270 milliseconds. Okay, so we somehow there is no name of the router mentioned on the first 8 nodes, but then we go to Giant. We entered Europe on the 9th node. That's what we know. Okay, so but we don't know the names of over here, so it's not really interesting. But anyway, Giant. We by the way, unlike the sanity of geography will suggest us that we should enter, Italy via Middle East or somewhere else, which is the right way to do it. But we are entering through UK, which is a very longer way to do it. So London, UK, and then Paris in France, and then I don't know where this is. This is Luxembourg or somewhere else. CH is, I don't know. Then Italy, then Milan, then Torino, and then we have request timeout. I have done this trace route before, and I know that it will not conclude. So I will stop it right here. It will go to 30th node because 30 is the maximum. And the reason it is not concluding, very interesting, why I chose to trace route www.polito.it. The reason it is not concluding is because the actual server of Politecnico di Torino, this one, it is blocking the ICMP messages. So trace route do not knows when to stop. If some middle router will block the ICMP message, trace route will just go one hop further. But if the final destination is blocking the ICMP messages, trace route don't know when to stop because there is a particular signal from the final destination which stops trace route. For example, let's do a very short trace route, very short, just google.com again. So you will know that it will stop eventually when we will have the final message from the destination. We will study in ICMP what happens when the destination sends something that the source knows that this is the destination. Okay, so the messages that comes from the intermediate nodes, from these nodes, this one, this one, this one, this one, all these nodes, these messages are different, and the message that comes from the destination is a different one. And that message tells the source node that this is the point where you have to stop. You reach the destination, and if the destination is blocking the ICMP messages, you actually don't know when to stop. So you will keep trace routing until you reach the maximum number of hops, which is 30. Okay.
What I wanted to ask was, so when it reaches the destination, if the destination blocks the ICMP, then we know that okay, this is the destination. But then does the destination still get the message telling that key message to the next hop?
No, there is no next hop. The path finishes. So all the next probes reaches the destination, but all gets denied by the destination. No reply, no reply, no reply. But the source will keep increasing hop count, just like the example of Polito.it. After 16, 17, 18, 19, up to 30, I just saved time. That's why I stopped. You can check it at your home. And you can see there is another trace which got complete right here. So, but the destination simply don't reply. So the source node never know that I have to stop right now. So it will keep probing until 30th hops, and 30 is the maximum. Okay, and this maximum limit is being kept because 30 is a very safe number. So usually, from anywhere in the globe to any other where in the globe, you'd never have a path more than 30 nodes. It's a very huge number. Okay. So you can see the next trace is finished. I've taken more time. I'm really sorry. I conclude here, and I can take any questions if you guys have, especially in the DL mode. If anyone has any question.
I just want to.
Yeah, please. Yeah.
When you talk about proving,
Hmm.
you know, okay, when a pin message goes, when it reaches the router, then isn't it that router's responsibility to tell the thing that the next?
It's not responsibility. Yeah, because the routers they are under the control of or the server. In this case, it's not the router who is blocking; it's the server. It's the web server of polito.it. Okay, it's the web server who is uh, who is serving the website of www.polito.it. That web server is blocking the ICMP messages. The server, the administrator controlling that server do not want the server to be overwhelmed by ping or traceroute or some other commands. So that's why the server will simply discard ICMP messages, and traceroute is an ICMP message. So that's why we as a user will never know that now is the time to stop traceroute, and we'll keep going until the 30th hole. Okay. Anyone has any question, जी?
सर
चलें
मेरा
जी
एक क्वेश्चन है
जी जी बताइए, मोहम्मद
सर
इकबाल
ये
बताइए।
सर मेरा मिडिल नेम इसमें नहीं आ रहा, हमजा नाम है तो
जी हमजा बताइए।
तो सर इसके अंदर ये जो कॉलम्स आते हैं ट्रेस रूट में, ये डिलेज के कॉलम्स हैं ना, तो ये कौन कौन से डिले होते हैं ये कॉलम्स को आप बता सकते हैं कि ये कौन से डिलेज होंगे जब वो कमांड मोड में आपने जब ट्रेस रूट की वो चलाई है
Right.
कमांड तो
Okay. First, let me repeat the question. The question is that the columns are reporting delay values in the trace route, and which delays are these? Because we have studied 4 components. This is the entire end-to-end delay. Okay. So let's say, for example, this value over here, this value, this 34 millisecond. Okay. This 34 millisecond is the delay of all the nodes in the middle and all the components on all these nodes. So, for example, on node 1, the processing, the nodal, the transmission, the queuing delay on node 1, and then on node 2, and then on node 3, and then on 4. The total sum of all the delays of all the components is this 34 millisecond. Okay.
so
It's
these
the
are total
end-to-end.
nodal delays.
This is end-to-end delay, not nodal. End-to-end delay, and the end-to-end delay is being calculated by summing all the nodal delays, and the nodal delay is calculated by summing all the components of that node. Okay. This is the end-to-end delay, right?
Yes.
Okay.
All right. Thank you.
Okay जी, any other question? ठीक है जी, मैं recording stop करता हूँ. Thank you so much. If there are any questions, we can take at the start of tomorrow's